Welcome back. This is a Tutor Wizard. I'm Adrian. Please subscribe right here. Hit the notification bell below. You can get notifications for this series and a bunch of other ones on our channel. What we're doing today is multivariable calculus. We're in chapter 3, which is vector calculus. This lecture we're going to do the law of conservation of energy, and then we'll phrase work using line integrals of conservative vector fields. And then so essentially we get to see why we've used the terminology conservative and potential functions for vector fields. Let's do that. We have an object with mass m, and we're going to describe our position with our parameterization of a position vector. And then what we have is, now in our terminology of physics, the first derivative, or the rate of change of position, is your velocity vector. And then the acceleration is the second derivative, r prime prime. And of course there is the jerk. He's always the jerk. That's what gets you in the car accident. The jerk, the rate of change of your acceleration, is what gets you. And you don't want that to be big. Hopefully it's 0, because your acceleration was only at most a degree 2 polynomial, and then the jerk will be 0 by then. Otherwise it'll be non-zero, and that's what gets you. What does Newton's second law of motion state? It says the acceleration, it's not the formula that we would get actually, and then I'm phrasing it in calculus. What he actually says is, what he derives is proportionalities, which is almost not discussed anymore, but the acceleration of an object at position r of t is directly proportional to the force at that position, f of r of t in our terminology, and inversely proportional to the mass. Solving that for the force, what that says is the force on the object is equal to mass times acceleration, which we call r prime prime. Now let's use that to derive the law of conservation of energy. First of all, let's do work and the law of conservation of energy. Let's quickly derive work over a force field moving a mass from point A to point B. Work is force times displacement. Displacement is the vector from A to B, this vector. And what we're going to do is approximate that vector along that displacement along the way. What we're going to say is that the displacement is approximately equal to the small arc length scalar multiplied by the unit tangent vector in the direction, or the unit tangent vector at that point. We're going to approximate the displacement as the small change in arc length scalar multiplied by the unit tangent vector at that point. Then what we're going to say is the work moving from A to B is approximately equal to force times displacement, which was the sum of all of those things. So the sum of the forces times the unit tangent vector times this arc length guy, which is a scalar multiple. W, therefore, the work is the line integral over C of f dot this unit tangent vector ds. Then we recall again that this unit tangent vector specifically was the velocity over its length, or r prime over the norm of r prime, and our arc length differential is the norm of r prime dt. Putting those in there, we cleverly get that these cancel, and we get that work is the integral from a to b of f of r of t dot r prime of t, which is our definition of the line integral over a vector field. So the definition of how we define a line integral over a vector field is work for physicists. Work is the line integral of that vector field dot dr. Now let's use that to derive the law of conservation of energy by moving between 2 points. The sum of the kinetic energy and the potential energy can't change as we move from A to B is what we're going to derive. And this is where we get the terminology. Okay, now we've seen that we have a vector field. Hopefully it's conservative. You'll see why later. But we have a vector field F. We want to know how much work it takes to move a mass from point A to point B in that vector field now. It turns out the work is the line integral of that vector field dot dr. This by definition is equal to the integral from A to B. Remember, this A is f of, or r of A, and this B is r of B. So our parameter goes from A to B. This is going to be f of r of t dot product with r prime of t dt. Now we know what F is from Newton's second law of motion. We know that this is the integral from A to B of F was mass times r prime of t dot r prime of t dt. And then the next move is this. M over 2, the integral from A to B of the derivative with respect to time of r prime of t dot product with r prime of t dt. It's like, what? How'd you get this? So what we're using is the product rule on this guy. Do it in reverse and we'll get this. If I take the derivative with respect to time of r prime of t dot product with itself, r prime of t, that's going to be by the product rule. This is properties that you can do, but it is true that you're going to get the product rule. That's going to give me r prime prime r of t dot product r prime of t. Leave that one alone. Plus, now I'm going to get r prime of t dot product with r prime prime of t, which is 2 r prime prime of t dot product r prime of t. So this thing is equal to twice that, or if I divide that through, I'm going to get this is 1/2. And what they're doing is saying these two are equal. This is now equal to this, see? So using dot product rules and derivatives, we cleverly get this. Why did I do that? And why do they want to see this move? Because this is great. Now what I'm going to use is the fundamental theorem of calculus. And this is going to be m over 2 r. Also, this is the norm. R prime dot r prime is the norm of r prime squared. So this is 1/2 norm of r prime of t squared evaluated from a to b, which is going to equal m over 2 the norm of r prime of b squared minus m over 2 the norm of r prime of a squared. And remember, r prime is velocity there, so this says the work is going to be m over 2 the norm of the velocity at b squared minus m over 2 the norm of the velocity at a squared. This is one derivation of what work is. If you know anything about physics, this quantity m over 2 the norm of v of t squared is called kinetic energy. Kinetic energy is defined as 1/2 mv squared. The speed, the magnitude, technically speaking. Physicists are lazy. We're going to be technical. We're lazy with units. I didn't use units anywhere. There should be units, foot-pounds or something. How much work did you do? I don't know. What does that give us? This gives us kinetic energy. If I phrase that this way, let's move that up and see what work is. This quantity, m over 2 norm of v squared, is called the kinetic energy. So we're going to let it be called Ke of t. And what that says is we just derived that the work in a force field moving a mass m from point A to point B is equal to the difference in the kinetic energies at these points. Now what I'm going to do is derive the work in terms of potential energy, and then we can set those two equations equal to each other and get the law of conservation of energy. If F is a vector field such that we have a function of two variables such that its gradient is this vector field, then we notice that the line integral of f dot dr is going to be that gradient, which now we can use the fundamental theorem of line integrals to do f of r of b minus f of r of a. In particular, in physics, we're going to call potential energy of a mass p of xy. And that's going to be negative of this gradient of whichever vector field you're in. If you have a vector field such that there is a f where we have this gradient is this vector field. I know it's confusing, there's a bunch of things going on here. We're going to call the potential negative of little f of x. In particular, that means that the gradient of f is negative the gradient of the potential, or the change of the potential. What that tells us is I can derive another formula for work in terms of potential energy by the fundamental theorem of line integrals, and the fact that we define this potential energy this way, we get that the work is f dot dr, which is now negative the gradient of p dot dr, the potential, which is by the fundamental theorem of line integrals, what they have a gradient, this is the negative here, and then we get the potential evaluated at the point B minus the potential evaluated at the point A. I distribute the negative through, and I get that the work now is, in terms of potential energy, is the potential of A minus the potential of B. Putting that together, Hypatia says if two things are equal to a third thing, they themselves are equal to. So the potential energies work equal to the work, and the kinetic energy is equal to the work. So the potential energy expression and the kinetic energy expression are equal to each other. And let's see what that says. It says the law of conservation of energy. Now we have the full derivation of the law of conservation of energy and why they started calling our mathematical terms the way we did. We took them from the physics people, and then we just run and systematically use mathematics and that language to prove things about these mathematical constructs, which are derived always from physics. Physicists want to know how energy works, but moving things between moving this pen from here, oh look, gravity took care of it apparently, but then moving it from here to here, now there had to be work done picking the pen up. So I just picked a mass up and the A was there, and then now here's B. How much work did it take to move that? What it's saying is, in terms of kinetic energy, the work done is the difference between the kinetic energy down there and the kinetic energy up here. And now the work phrased in terms of potential energy is actually going to be the reverse. It's going to be the potential energy down there minus the potential energy up here. If I set those things equal to each other by transitivity of the equals relation, I get that these two expressions are equal to each other. Getting rid of the negatives and moving everybody over, I see that the potential energy plus the kinetic energy, or the sum of the energies at this point, is equal to the sum of the energies at this point. And what that says is total energy didn't change from point A to moving the mass from point A to B. The kinetic energy and the potential energies have changed, but the total change in the system has not, and this is what we call the law of conservation of energy, and this is where we get the terminology of a conservative vector field, and the little f, such that his gradient is big F, is a potential function, because we're trying to phrase the terminology mathematically as constructs for describing the physical phenomenon of the law of conservation of energy. Let's do an example of that. All right, example, and then we're done finally. The applications of the fundamental theorem of line integrals is I don't know which one comes first, the chicken or the egg, but the law of conservation of energy is what we were trying to understand. Mathematics is the language that we're going to use to do that. Find the work done moving a mass m from point A00 to B21. Find the work done moving a mass m from a point A00 to point B21 in the vector field f of xy, which is x squared y cubed comma x cubed y squared. What do we have to do to solve this question? This is the hardest part, and you have to get a map, and the more you do this, then the more comfortable you get, because I can see a route from the horrible question all the way to the answer, and I have several steps in mind of what I'm going to do and chop it up and make it simplified. First, what I'm going to notice is I have to do the work done moving a mass from A to B in a vector field. We know that first of all now is the work is the integral of f dot dr over that curve C. I would really like it if that function was a conservative function, so he's a gradient, and then that will be the integral of the gradient of f dot dr. And then that, by the fundamental theorem of line integrals, is going to be f of r of b minus f of r of a, and that's a calculation when we're done. And remember, these are scalar functions, so you're just putting numbers into something that's going to look like this, and then we get an answer. That's where we're going with that. Step one, I need to show that this function carefully is conservative. Then I have to find that conservative function. Then I'm going to use it in the fundamental theorem of line integrals to compute this work. Let's do that. X squared y cubed and x cubed y squared are polynomials in x and y, and therefore f has domain r squared, which is simply connected. That's the first condition of checking if those partials are equal, then conservative. So first I check, and I've given myself a nice polynomial in an example. So that's the domain is r squared, which is a simply connected domain. And now is the conjunct. The partial, this is p and this is q. The partial of p with respect to y is the partial with respect to y of x squared y cubed, which is what? This is going to be 3x squared y squared. The partial of q with respect to x is going to be of x cubed y squared, which is going to be 3x squared y squared. Oh, look at that. They're equal to each other. This fact and this fact says that f is conservative. Good. Now that I know it's conservative, let's do the steps to finding that conservative function, or little f, such that the gradient of little f is big F. All right, moving that up, what does that mean? I now know that f is conservative. That means that there's a little function f of x, y, such that its gradient is f. Those two vector functions are equal if and only if their components are equal. So this says the partial of f with respect to x has to equal p, and the partial of f with respect to y has to equal q. Then from that, classically, I take this one, I integrate with respect to x, which gives me f of x, y is going to be the integral of the partial of f with respect to x dx, that guy, which is equal to the integral of x squared y cubed dx, which is 1 over 3 x cubed y cubed plus a function of y. Now, again, remember, normally we would put a constant of integration because a constant derivative of constant is 0. Now, if I'm taking the derivative with respect to x, any term that has y will become 0 also. And then, now what am I going to do? Now I'm going to use this equation to find out what that guy is, and then I have my function. This immediately already tells me that my function is 1 over 3 x cubed y cubed plus a function of y. Once I find that, I'm done and I have my potential. 2. Now I take the partial, and now I have f again, and I suspect I know what f is. I'm going to take the partial with respect to y and make it equal to this guy. That says fy, the partial of f with respect to y, is going to equal what? Oh, magically the 3 will cancel, and I'm going to get x cubed y squared plus h prime of y. On the other hand, it equals this. Oh. So that says that h prime of y is 0. Integrating that says that I'm going to get h of y is a constant of integration. What does that say for us? That says f of x, y is equal to 1 over 3 x cubed y cubed plus k. We can take k equals 0. Or if you don't want to, you'll see when you do f of b minus f of a, this is going to go away. But our function is this now, setting k equal to 0. I now know, because I've done this before and I've mapped it out, and which makes it so much easier. The problem with life is we have to live it forwards, and we can only understand it in reverse. So I'm doomed to do this in forwards. I have to do the problem forwards, beginning to end. But once I've done it a few times, I can analyze and reverse it. I now know I'm going to use the fundamental theorem of line integrals, which says it has to be f of b minus f of a. So I'm going to calculate and chop those up before I put it in the soup again, because I already know where I'm going. So f of b to 1 is going to equal now just this function, 1 over 3 times 2 cubed times 1 cubed, which is equal to 8 over 3. And f of 0, 0 is equal to 0. Now here's the slickness of the fundamental theorem of line integrals. The work done moving that mass m, which coincidentally is independent of the mass, is moving it from a to b in this conservative vector field f, is equal to the line integral of c over f dot dr, which is equal to the line integral over c of the gradient f dot dr, which is, by the fundamental theorem of line integrals, is equal to f of b minus f of a in lazy notation, which is 8 over 3 minus 0, which is 8 over 3. Something foot-pounds, I don't care, physics. Please subscribe right here, hit the notification bell below. I'll see you next time. Wizards do conservation.